It's my pleasure to introduce the next speaker. So, Ada Abay was studying quantum computing with researchers from at MIT and the University of Oxford already at 13. He completed quantum school at University of Waterloo, worked at Boston Cube PSI and developed a quantum chemistry project and technical report and won the first place award at National Science Competition. He's an ambassador at Yale Young Global Scholars and a section leader instructor at Stanford Code and Place. He's studying computer science at the University of London. He's the founder of KuCan and scaled the company to three successful cohorts, diverse services, partnered with four major players, Classic, Hippo, KuControl, and B2B. And he will talk today about the quantum shift, understanding the technology and creating an ecosystem. So quantum computing is evolving from theoretical promise to practical possibilities, what we just have seen in the talk before. And when it comes to the need for a broader ecosystem of learning and applying. This talk explores where quantum technology truly stands today, separating progress from perception and hype. So we will discuss how quantum services are adapting to prepare both individuals and organizations for a quantum-ready world, from emerging enterprise use cases to the growing importance of accessible learning pathways. We will examine how understanding the technology, effectively using its tools, and nurturing the ecosystem are equally vital, shaping the future of innovation. So thank you very much for joining, Ada. And I give it from here to you.
Thank you so much for the kind introduction, Sandra. And also, I'd like to thank the Cue It Up for their kind invitation about having me over here. It's great to seeing all of you and having this talk here. So let me just share my screen. Um, I hope you're able to see now.
This looks good.
Okay, great. So as Sandra said, my talk will be focusing on the quantum shift, understanding the quantum technology and creating an ecosystem. My name is Arda.
Ada? Ada?
Yep,
Sorry, at the
yes.
moment we see a slide in the slide. Oh, okay. Now the
Okay,
view.
it's better.
Okay, yes.
Okay, amazing. Okay. So I'm the founder of QCan. At QCan, we're positioning ourselves as the center of quantum computing, providing individual quantum computing programs, quantum resources, services, and also enterprise services in a whole in one place. So we know quantum computing is evolving from the theoretical promise to practical possibility. Starting from 2019, we've seen some rapid growth in the breakthroughs that are happening from quantum computing. And when it's coming to the need for a broader ecosystem of learning and actually applying this technology, it's crucial to have the right players in the zone. So with this talk, we'll be exploring where actually quantum technologies truly standing today, separating the progress from the perception and the hype. So we just want to see how the quantum idea evolved, where are we standing truly. We're going to back that up with some misconceptions, some data, and also some statistics coming from the larger players in the industry. And afterwards, we're going to discuss how quantum services are adapting to prepare both the individuals and organizations for the quantum-ready world, and how we're also supporting that as QCan. Okay, so here you can see a quantum computer. On its own, it's a striking piece of technology, but it's also a window into the future of computing. They approach problems very much differently than classical computers. And over the next slides, we're going to explore some key concepts, hot topics, latest advancements, misconceptions, and interesting facts of this breathtaking technology. So we're going to start the talk with this first part. And after that, we're also going to talk about the building the ecosystem and how we position ourselves into this as QCan. Okay. So before actually diving into quantum computing, I also wanted to bring this on the table. Like, why not stronger classical computers? Why aren't we actually progressing on the development of classical computers? Because many great things are happening there. And yet we're still on parallel working in a different kinds of technology, quantum technology, that's taking the power from the quantum mechanics. So the key here will be hitting the limits, as I had like meetings with the biggest company founders in the industry, The key point here is about actually hitting the limits. So the transistor size approach to physical limitations, where quantum effects blur the line between on and off states. So as we know, quantum computing is storing the information with qubits, which are quantum bits, and they're taking the power from quantum mechanics. However, the same isn't going for classical bits, as they can be either one or zero, on or off. But as they're getting smaller and smaller, which is also correlated to the Moore's law, we're actually being in a place where we're stretching the limits of these classical physics, and it's not going to work any longer. And smaller transistors also cause higher leakage and power use. And this is reducing efficiency, which is something the corporates, large enterprises definitely do not want. And smaller chips consume more energy, making heat removal harder and still hurting performance and decreasing the efficiency. So one of the points that quantum computing arise, although there are many perspectives out there, could be seen as hitting the limits. And I also wanted to show it in here. This slide is one of the ones from the QCAN's presentation. Okay, so now that we see the classical computers wouldn't be actually working, we can start off with quantum computing. I don't want to make this like a tutorial, but rather a storytelling. So we're just going to swiftly go over what is quantum computing, some key concepts, and then move on. So the fabric of our universe is inherently quantum mechanical. With the problems natural systems are solving, they explore the area of options all at once and change, adopt. And much like the beauty and adaptability of nature, quantum computing utilizes quantum mechanics to perform calculations and responds to the conditions around it. This is unlocking breakthroughs for the most difficult challenges of tomorrow and enabling a new era of computing, like offering significant speedups for solving complex problems and tackling ones deemed practically unsolvable, or revolutionizing scientific research, transforming key industries, and unlocking new possibilities for a more efficient and secure future. So one discrimination could be made here is about quantum computers not actually solving all kinds of problems or providing outputs on all sort of tasks, like maybe opening up the browser or being watching over Netflix, but rather they're quite very powerful about specific types of problems that are giving us that advantage. And when we use quantum mechanics to perform computation, we call this as quantum computing, and we hope to gain advantage with this. Okay, so before discussing the advancements and impacts of quantum computing, I want to briefly introduce the core ideas of quantum mechanics, also to make this talk very interesting for everyone. So because these ideas are exactly what give quantum technologies their advantage. So let's start with a small game, ship or heads. In ancient Rome, coin flipping was called Navia haute caput, ship or hat, because the one side of the coin carried a ship and the other called it the emperor's hat, as you can see from the slide. In England, it later became known as cross and pile. So who would have guessed that such an old and simple game would become the perfect metaphor for understanding the most fundamental concept of quantum mechanics? So when we flip a coin, we say heads or tails, but that's only once the coin lands. While it's spinning in the air, it's neither fully heads nor the tails. It exists as at a probability of the both states at the same time. And that in-between state, the gray zone, is the simplest way to imagine the foundation of quantum computing, superposition. So how about we put the coin aside and design something a little more complex? A coin in midair already gives us the taste of both at once, but quantum mechanics doesn't just stop there. In the quantum world, particles don't just have uncertain states. They exist in multiple states simultaneously until we look. To make this abstract idea a little bit more concrete, physicists created one of the most famous thought experiments, Schrödinger cat. So you probably may have heard of it, but in case you don't, that's still completely fine. It's not meant to tell us anything about cats, though. It's meant to stretch our imagination just enough to understand what superposition really means. A system that's not one thing or the other, but combination of possibilities that only become definite when we observe. In Schrödinger's original formulation, a cat, a flask of poison, and a radioactive source are placed in a sealed box. If an internal radiation monitor, such as a Geiger counter, detects radioactivity, meaning a single atom being decayed, the flask is shattered. It's releasing the poison, which kills the cat. If no decaying atom triggers the monitor, the cat remains alive. So mathematically, the wave function that described the contents of the box is a combination or quantum superposition of these two possibilities. Yet, when we look in a box, one sees a cat either alive or dead, not both alive and dead. This possesses the question of when exactly quantum superposition ends and reality resolves into possibility or the other. And a fun fact, actually, although originally this experiment was decided to critique the Bohr and Heisenberg's experiments, Schrödinger's seemingly like paradoxically, this thought experiment became part of the foundation of the quantum mechanics in QC 101 in our individual program of QCAN, the beginning one. We also like touch into this concept very much in detail with the lecture and the laboratory. So as a result, Schrodinger's cat has had an enduring appeal in the popular culture. So now that we have a clear, although it's non-mathematical, it's still clear intuition for superposition, we can move to the next step. So what happens when two quantum systems share this property together? This is where qubits reveal their power. So now let's look at the superposed states can become linked in a way that has no classical equivalent. And I'm talking about entanglement here. So regarding that, I always used to like have the storytelling in mind. This is something we're doing with our instructors and super talented TAs too. So let's go over a scenario. Imagine we have Alice and Bob. Each of them has a closed box with a boxing glow inside. They're standing in completely different galaxies. Neither of them know which glow is left-handed and which one is right-handed. So now here's a twist. These two glows were prepared in a special quantum way. They're not decided yet. They're not independently left or right, and they exist as a joint possibility. So when Alice opens her box and sees a left glow, Bob's glow doesn't just change, and it was never independent in the first place. The moment Alice looks, the global system becomes definite, and Bob's glow becomes right-handed instantly, even from another galaxy. So nothing travels between them. There are no signals, there are no messages, just a single shared state revealing itself from two locations. So this was the storytelling, and now the scientific part. This is the quantum entanglement. When two qubits are entangled, they no longer have their own separate states. Their probabilities are defined only collectively by a single combined quantum state. Measuring one qubit doesn't send information to other, it simply just collapses the shared state into one of its allowed outcomes. So in classical physics, Alice's globe and Bob's globe would be predetermined and independent. And in quantum mechanics, entangled qubits behave as one system, even across extreme galaxies. This correlation, stronger than anything classical physics allow, is what Einstein called spooky action at a distance. Now that we just passed Halloween, I think it's quite appropriate. And it just forms the backbone of advanced quantum communication and multi-qubit quantum algorithm. Actually, we just had an announcement regarding that coming from IBM about having entanglement in large quantum algorithms. Okay, so before we talk about the latest developments in quantum technologies and step into the ecosystem, uh, and also talk about where we truly stand today, I want to take a moment to focus on a concept connected to this year's Nobel Prize in physics. It's about quantum tunneling. So we talked about superposition, entanglements, and quantum tunneling is one of those ideas that sounds almost impossible from like a classical point of view, but we're talking about quantum here, and yet it lies at the heart of many, many quantum phenomena. So before we look ahead, let's zoom in on tunneling itself and understand why it really matters. So in everyday life, our objects behave in predictable ways, right? If we throw something at a ball, it stops. And if we roll a billiard ball toward the edge of the table, it doesn't just suddenly appear on the other side. It just bounces back. And that coming from that, classical physics feels solid, literal, and intuitive. But if we shrink the world down to quantum scale, and those intuitions break instantly, like their particles don't always stay like confined. They always stay exact. A quantum particle facing a barrier, it shouldn't be able to just cross, can sometimes be found on the other side, as it briefly borrowed a path that classical physics just doesn't have. And this phenomenon called as quantum tunneling, it isn't drink. It it's not a speculation. It's a measurable effect that shapes everything from the nuclear reactions powering stars to the operations of advanced electronic quantum devices, as we saw with the announcement this year. And this year, Nobel's Physics Prize highlighted research showing that tunneling isn't restricted to just tiny isolated particles under the right conditions. So when we meet the conditions there, even larger and more complex quantum systems can display these behaviors. And quantum tunnelings remind us that, like at the deepest level of nature, the rules are far stranger, as we generally like hear this from quantum computing, and they're far more powerful than our everyday experience suggests. Really. Okay. Um, and I also wanted to add this here, just because I feel that it's quite very important. The Royal Swedish Academy of Sciences is like regularly announcing Nobel Prize, but in 2025, the physics has been awarded to, as you can see, John Clark, Michael Deveray, and Joan Martins. So they're pivoting and pioneering experiments. They actually carried back in 1980s show that phenomena like quantum tunneling and discrete energy levels can emerge in devices made from vast numbers of electrons. So this work fundamentally challenged the long-held assumption that quantum stops where classical begins. Quantum mechanics tells us that particles can sometimes cross barriers they have no classical energy to overcome. This is the hallmark of the tunneling. So before these researchers, their results, such effects had only been confirmed in systems involving individual particles or atoms. But this actually was the first time that we could see in larger scale. And although the world moves faster today, many scientific awards still follow like a written about awarding these important prizes years later, waiting for long-term validation, replication, and influence before honoring the word. So in this case, like the delay underscores just how ahead of their time these experiments and these wonderful scientists were, and how profoundly they reshaped our understanding of the quantum classical boundary. Okay, so we have foundations in our pocket. Now we can talk about a overly hyped concept. We can also like discuss if how you feel about this, if you feel this is actually something coming, or are we already there? So we define quantum computing as a new approach to calculation that use principles of fundamental physics, like superposition, entanglement, quantum tunneling. And we're using them to solve extremely complex problems very quickly. And when we talk about quantum supremacy, we mean the moment a quantum computer can solve a problem that no classical computer can solve in any feasible amount of time. It's a milestone in science, and not just about the speed, but about their fundamentally different way of handling information through these weird phenomena like superposition, entanglement, tunneling. And it's also important to remember that. Oops, just a second. Okay. Yeah. Okay. It's also important to remember that like the supremacy is a proof of concept. It doesn't mean the computer is performing a useful and commercial task yet, as we're just going to talk about this with the next slides. The real game changer for our daily lives, as I happen to believe this, will come when quantum computers can tackle problems that are both quantum in nature, however, also commercially relevant. And until then, I believe supremacy shows us the incredible potential where we're gaining a quantum advantage, but the real impact is hiding when we measure it by the problems that we can solve that are actually matter, that are affecting our everyday lives. Okay, so we talked about what quantum is and what we mean by supremacy. Well, let's turn to one of the important recent advances in quantum computing, Google Quantum AI's Willow announcement. So this chip represents a leap forward in quantum computation and gives us a chance to look more closely into dynamics shaping the industry. And to keep things clear, I'm going to summarize the technical announcements into like two important takeaways for you so that we can continue and move on with more exciting things about quantum. So here we see a remarkable feature of Willow, exponential quantum error correction operating below the threshold. So in simpler terms, this means that as Willow uses more qubits, its error rate doesn't grow. Normally, like this was the way we got used to. When the qubit increases, the errors are also getting increased. But for Willow, it actually shrinks. The system becomes more stable, more reliable, and in a sense, more quantum. So why is this so important? Because error correction has always been like the biggest challenge in building practical quantum computers. For decades, many, including scientists and founder CEOs, believe scaling up would only make the errors worse. But Willow showed us the opposite. Scale can lead to scalability. And this development is like a significant step toward building larger and more capable quantum system. And last but not least, like the media and generally many journals decided to like focus more on this because it's like if you'll admit, it's much more exciting. The slide shows like Willow's performance on random circuit sampling benchmark. Willow completed the task in under 5 minutes. And just to compare, one of today's fastest supercomputers would need on the order of 10 to the power of 25 years. That's like about 10 septillion years. So the point here is not like the exact number itself, but the scale of difference it represents. It demonstrates a clear separation between what's possible with classical machines and what can be achieved with quantum computers like Willow. And the result marks Willow's strongest benchmark to date, and it provides an important reference for measuring progress as we uh, move forward in the field. So, and just to put that number into perspective, we have the slide for you. That's 10 million trillion years. A time scale beyond anything we encounter in physics and vastly longer than the age of the universe itself. So this was also something noted in Google Quantum AI's report. Some believe it was a little about just like attraction reasons, but it's still there and it's something quite unique. And I believe you're also going to find it interesting. The situation leads to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a more multiverse, a prediction that first actually made by David Dosch. Okay, and this chart shows how quantum computers have progressed solving tasks that would take classical supercomputers, as you can see, an astronomical amount of time. And if you like notice there how Willow stands out, highlighting the rapid advancements in quantum performance. And here in the visual, we see that Willow has solved the RCS, random circuit sampling. Um, uh, this is actually a task that's like extremely difficult. But as you can see here, it's a little bit limited in the being practical to use. The solution time is quite impressive there, which is why media often focuses on this aspect of the Willow. However, for the quantum industry and academia, and for QCAN too, because we're dealing in, like we're in communications with both the industry and learners, customers just wanting to get into quantum computing or improve their journey. What's truly promising here is, I believe, about the quantum error correction. Of course, the promise comes with significant challenges that still needs to be overcome, but like in here, we can believe that sometimes just losing the perspective, or like at least getting away from the perspective of the media just for a second and focusing on the real developments, breakthroughs, is also something valuable to just like progress on your journey. Um, all right, so after reviewing the dynamics of quantum computing, the state-of-the-art development coming from Google, uh, we can also like continue with another announcement made by Google very lately, actually. It came this October, and I also wanted to add in the presentation. So now we're looking at one of the most important milestones in quantum computing this year, Google's verifiable quantum advantage using Willow chip. So it's connected there. The experiment centers around a protocol called quantum echoes. The idea is simple to state, but extremely powerful in the practice. So first, the quantum computer runs a long sequence of operations forward in time, creating a complex quantum state. And then one single qubit is deliberately distributed. And after that, the entire sequence is running again, but in reverse. And at the end, we're getting the echo. So and here, the quantum echoes on Willow shows us that we've crossed that threshold, and we now have a device that operates in a computational regime classical machines cannot keep up with. It's like a sign that we're not just exploring quantum computing anymore, but we're entering a stage where quantum systems begin to reveal capabilities the classical world cannot match, but it still needs to be done with the with like the real world use and actually having an effect to our everyday lives. Okay, I think I also got a chat message. That's actually a very nice question, Sophia. Thank you so much for bringing that on the table and your interest. So the like separating progress from what we're expecting with quantum computing and the hype is quite very important. So this is also something we're like deeply caring about. QKIN's QC 101, our Introduction to Quantum Computing program, in all of our services. So for that, we're like progressing everything with two perspectives: the theory and the practice. The theory comes within our understanding of these laws of quantum computing and how are we seeing that on the paper. And with the practice side, as you're also going to like see that with the next slides, we're partnering with like the leading players in the industry to show what quantum computers are actually capable of doing. So what I would say is it's important to know that quantum computer holds a lot of promise there, but they're not going to change or have direct effects to everyone's lives. Currently, they're like they hold the promise to solve specific types of problems in a faster way or in a way that classical computers cannot, like simulating the molecules. So I believe this is the key to hold here. And what I would say to just like overcome this or actually witnessing this is to try out actual quantum platforms by yourself. So we're like partnered with Classic, Keep Quantum, but there are many platforms out there to see some actual use cases of quantum computing. Like I would be very delighted to give detailed answer, but also since the time is limited, I have to just say this. Hopefully that was helpful though. Also another message to perform any concepts and community quantum for surgery. It's like really nice to hear about your project DEMS based on Cubo. It's like really nice. Like most quantum. Okay. Like I would be happy to like talk to you about this. Maybe at the end if you have the time, or afterwards you can also contact with me too. Like currently, I may proceed with the presentation, but afterwards, feel free to just describe your project to me over LinkedIn or maybe email. Okay. And so with the previous slides, we looked at Google's Willow announcement. It was like a real example of what a single company can build when they focus on deeply one architecture, which is superconducting in that case. But Willow is only one branch of the much larger ecosystem. So Globally, as you can see from the image, dozens of companies are developing quantum computers using very different physical approaches. Some rely on superconducting qubits, like Google, others maybe on spins in silicon, some on trapped ions or neutral atoms, and some take completely different route with photons, or as Microsoft is doing, topological qubits. So what you see on the slide is not a list of competitors, as I like to say, but it's a map of parallel encodes bets. So like each technology has strengths, weaknesses, and engineering bottlenecks. And like we don't yet know which one will carry us all the way to the fault tolerant machines. And yeah, this is like the overall picture. These are, I don't like to call them as like competitors, but um, I would say different kinds of players in the game. Okay. So we were talking about quantum computing, its promises, breakthroughs, but now we can also, as we're like having the main theme of the presentation on that, talk about maybe the speed bumps for quantum computing. So here I use the term speed bumps intentionally, like how Michio Kaku did, instead of calling them as maybe problems or troubles. So there are temporary slowdowns, not things that will stop us in the long-term progress of quantum computing. So first, we have the high error rates. Qubits are still generally prone to errors, which make running reliable computation challenging in most systems. And secondly, we have the coherence and the noise. This is like slightly different. Here we're talking about qubits losing their quantum states due to environmental interference, and which is like limiting the um, long computations being run. And finally, we have scalability challenges. It's about building system with hundreds or thousands of qubits, and it's still remaining a major technical hurdle. It's slowing down the practical applications, but progress by progress over the, I wouldn't say years now, I would say months, because we're hearing different kinds of news in the quantum computing industry now. Every week almost, it's getting like closer and closer. So now I also like would like to quickly look at some facts that might help clarify common misconceptions about quantum advantages and these speed bumps. Okay, so here we see minus 273.135 degrees Celsius. This is the temperature to operate many quantum computers. Uh, like basically, to operate many quantum computers, they need to be cooled to just 15 millikelvin. But it's also like important to note what actually needs to stay this cold are the qubits themselves, the tiny chip at the heart of the system. So all the surrounding structure you can see with the first picture and the slides, basically about the superconducting qubits, the fancy hardware and enclosures are basically just like a sophisticated cooling system, keeping the qubits at that extremely cold temperature. And there are other approaches to, like we saw with the previous slide, like neutral atom systems that can operate closer to room temperature, but they still face some technical challenges. So systems like Willow superconducting qubits operating at just 15 millikelvin, almost at absolute zero, like where the motion just like literally stops, show what's currently possible, giving us a glimpse of the future of quantum computing in that case. And now looking at the scale of like what's needed to perform a practical complex quantum computation, estimates suggest we'll need around 20 million physical qubits. So just to make a comparison, Velo superconducting system has 105 qubits. So this is highlighting both the impressive progress we've made over the years, but still the massive gap we have that remains before having a large scale, fully error corrected quantum computers becoming a reality. But this, like, I would like to stress this doesn't mean that we're away from having an actual quantum computer working and we're just still waiting. Quantum computing has like use cases that are actually working right now, and we're witnessing that with our industry partners at Kukin and giving those license about these platforms. We just have a long way to achieve where we want to be, but isn't it this technology and science all about being in that journey? And here we see that to create like a single reliable logical qubit, we may need up to 1,000 physical qubits, and physical qubits that are actually hardware on the chip, while logical qubits are what we use for error-corrected, dependable computation. So essentially, many physical qubits work together to form one stable logical qubit. Okay, and this is like an interesting fact. I happen to like reading those insights and articles from McKinsey quite much, and also wanted to give it here. And it's also completely free. If you like, feel free to just go into McKinsey and read some articles, insights about quantum computing, especially if you're interested in the business and the valuation aspects of quantum computing more. So investments are like surging in quantum computing, and innovation is accelerating. And analysts project the quantum market could reach to $100 billion in the next decade. And this is a clear sign that the field is moving fast and the future is looking promising. So with the previous three slides, we were a little bit pessimistic, but this is also one of the facts coming from McKinsey, a forecast. And even today, the quantum computing market is like already valued at around $3.5 billion. And with ongoing advancements, investments, it's clear that the future is already arriving. And I would like to also like discriminate one thing here. When we talk about quantum computing, it's actually only a part of the quantum technologies. So when we say quantum technologies, we mean quantum computing, we mean quantum sensing, quantum telecommunications, and those have different kinds of use cases and actually approaches. So in general, I would like more delighted to use the term quantum technologies, but in this talk, because of like also like the audience and the general interest, we're basically focusing on the quantum computation. Okay, so we got deeper into quantum fundamentals, hardware breakthroughs, speed bumps, quick facts, and maybe we can also like have an eye on the just like leaving the lab behind and looking into the real world. So the real part surprises many people outside the field is about quantum not waiting for the future. Um, as you can see, the world's largest organizations are already investing, not because it's just fashionable or cool, but because certain high value problems simply just cannot be pushed further with classical tools. And when you look at the landscape, you see a pattern, like you see finance, energy, aerospace, automotive, pharma. I can see manufacturing, telecommunications, defense. So the sectors with like the highest computational pain points are moving fast. And these companies aren't just deploying full quantum solutions today, but they're building like teams, forming partnerships, running proof of concepts, and preparing their infrastructure to hybrid quantum workflows. And this is opening up a whole new kind of workforce and area to join in the quantum computing industry if you're interested in such. And the important thing here is like once enterprises start, they just rarely go back. Quantum capability becomes part of their long-term innovation strategy there. And in here you can see like diverse sectors. Every one of these sectors faces optimization bottlenecks, simulation limits, security challenges that quantum technologies can like directly influence. So for example, just to give some like examples, in finance, it's about risk modeling, portfolio optimization. In energy, it's grid stability, battery chemistry, and carbon neutral materials. In logistics, we have manufacturing, scheduling, routing, real-time resource allocation, as we're like seeing that with the platforms and actually use cases. And like while being in our live sessions about the industry parts, I like very much being involved in all these. I like remember how exciting this is to witness technology being developed and to see like actual use cases there. And in healthcare and chemistry there. It's about molecular simulation. This is an example that we're especially giving because it's basically something almost impossible for classical computers to do, but we're able to do it with quantum computers. So basically, the key message is this: like quantum is not one industry's technology, but it's a cross-sector accelerator. And Understanding that landscape is exactly why QCAN exists, to train the talent, guide the organizations, and build the global quantum ecosystem that will actually use these technologies. Yeah, so here you can see slides from one of our QCAN's presentation. So, and here we see like a missing link, a gap in the quantum transformation. So academia is doing many uh, improvements, curriculum additions, and actually like following the latest breakthroughs in quantum computing and integrating that. And the industry is like keeping going on and on. And nowadays, even like every week, we're hearing a different announcements coming from quantum industry, even if they're like coming from different kinds of quantum hardwares, quantum computer types, they're all exciting. And the world is like investing billions in quantum technologies, as like McKinsey also forecasts coming from their sources, coming from to the places like quantum technology, quantum communication, quantum sensing, and quantum computing. There's still a gap between the education and real industry application. And this is about like lack of core concepts, lack of practical training, and unified learning platforms. So we've taken a practical and fascinating dive into quantum computing, and it's been a real pleasure exploring these concepts with you. However, like as large companies drive the quantum revolution forward, it's critical that individuals, students, employees, executives, professionals, as well as organizations and enterprises build this quantum awareness, make use of the industry services and connect, engage with the community, and even like earn certifications. This goes for both individuals, but also large groups, maybe coming from enterprises. So with that being said, I actually cannot think of a better moment to introduce you to like our what we're doing at QCAN, our flagship programs, and our services. So let's just move into the next slides to go over them. So this is QC 101, the first pilot concepts that we were doing at QCAN. So in the first place, I can talk a little bit about QCAN. So we are positioning ourselves as like the central ecosystem of quantum computing. We're providing individual learning platforms, enterprise learning platforms, learning programs, and quantum computing services there. And we started this journey with QC 101, Quantum Computing 101. We have conducted two cohorts so far, and like with that proof of concept, seeing what we're doing, we're now turning it into a whole structured way. And I'm the founder of this company. So QC 101 is like combining live tutoring with this goes for lectures, laboratories. Okay, this goes for live sessions, self-paced videos, and also like the industry sessions. So the main thing is we wanted to make a program that goes for like everyone, starting from the beginning of quantum computing, and basically covering everything about the core concepts, and at the end, like in parallel with the industry applications. So therefore, we wanted to combine the live lectures, live laboratories, and industry exposure there. So I would like to like hold there just a bit, and afterwards keep going on there. So for that, we've partnered with Classic. So through our partnership with Classic, learners enroll into like taking our services can access to Classic platform, and this is bridging world-class tools directly to the program. So just to tell you a bit about this, this is actually like a real quantum platform where you can execute tasks on quantum computers and see the outputs. But Classic does this a little bit differently. They're not just looking into gate-based coding, but they're doing this on a high-level way. So it's all about this. Oops, sorry. It's all about designing of novel quantum algorithms, optimization of these quantum algorithms, novel quantum algorithms, and analyzing them and executing them via Classic. So it's quite simple. It's all high level, and it's like a very easy to use platform to just navigate over these tasks. And we're quite delighted to have them as our partners at QCAN. And we also do have Kipu Quantum Hub. Let me also share my screen for that too. Okay. Okay, so hopefully you can see this. So this is about Cube Quantum Hub. So I'm just going to briefly go over the slides. So it's all about hardware distribution, access control, cutting edge algorithms, collaborations and co-development tools, and use case hosting. So with Cube Quantum Hub, you can basically see the app's use case demonstrations, visualizations of quantum application and use cases, quantum hardware and quantum algorithms. And it all has integrated in this like very user-friendly GUI. Oops. Okay. Yep. So this is also basically how Cube Quantum Hub works. Let me go back to the slides. Okay. So these are also snapshots from Cube's side. And we're also partnered with Q Control. Although like they have very like advanced quantum advancements, like their Fire Opal. We're partnered specifically with Black Opal, which I happen to call like the Duolingo of quantum computing. It's like interactive, it's easy to use, navigate, and it's quite fun to learn quantum computing with. So therefore, we partner with all these services to bring them in QCon's ecosystem. And our vision is to like partner with the leading quantum computing companies out there to bring all of them in one ecosystem, to provide learning resources, interactive programs, to provide solutions and educational programs to enterprises and companies, and to provide services like you're going to see with the upcoming slides to everyone, individuals. And we want to like get it all in a single platform. And it's also like combining the videos, documents, quiz assignments, expert industry sessions, and certification. So yeah, this is basically like how we define QC 101 in the first place. As you can see, we're like starting from the very beginning of quantum computing, and we're also covering the background, the foundational ideas, and afterwards how to like apply them into real world. So it's all about theory in here and all about the industry tools in here. So just to connect it with what we saw with the first slides, it was about like the idea behind quantum computing, but we talked about it in a storytelling way. And afterwards about the facts, the misconceptions, the breakthroughs in quantum computing. And we try to discriminate what's actually going on, where we stand at quantum computing from the hype, and like looking from all of that perspective for QC 101 specifically with two like successful cohorts, we ended up with here about combining everything in one picture in a meaningful way. Yeah, and to talk about some stats, we're quite delighted to like share that more than 97% of our learners found it transformative, and we had more than 600 learners from more than 50 countries and more than 50,000 interactions. So it's like quite rewarding to see that interaction and the willingness to learn about quantum computing, to step into that zone. And we like worked tirelessly to just like have those partnerships there, the most quality resources there, and to make the best way to like get into and learn quantum computing. Yeah. So this is like the overall picture we created. And we because we want to have it like an ecosystem, we are also like having those enterprise services licenses at the platform, but also we're providing some individual services like Q Network, where anyone can join there. It's completely free, and connect with peers all across the globe. Just discuss, share ideas, meet with different people, and just like develop your network and increase your connections in the quantum industry. And we also have the QNUT book, which is like a article and insight sharing platform. This goes both for individuals and enterprises separately. For individuals, we just don't want to share articles that are just like a news and summarizing things, but we want to have the we wanted to have the articles that are worth reading in the balance between the scientific accuracy, but also popular science and storytelling. So we're also continuing with that too. Okay, and we combined all of them under Q platform, which is like a central dashboard. So our vision is to have this platform when it's like anyone just accessing that will be all their resources to just learn, apply, collaborate, and basically like access to anything about quantum computing from there with licenses, services, and more. So this was how we envisioned the quantum shift, how we separated the theory from the hype, and how we like turned that into one ecosystem that's covering everything for people from different kinds of background, different kinds of needs, with one common goal, just like getting into quantum computing, learning more, doing more, and being part of this revolution. Okay, that wraps up my presentation, but it's just right in time. So thank you so much for listening. So some of these slides were coming from QCAN. So these are the info of QCAN. And if at the time allowed, I'll be happy to like chat and collaborate with you, answer questions, but also feel free to send me a connection over LinkedIn or write me a message. I would be also happy to help you over there too.
Thank you, Arda, for an excellent talk.
Thank you.
And yeah, clapping, the virtual clapping. So we got some questions. So you mentioned
Sure.
that error correction is currently the biggest challenge. Which error correction approach do you believe will become practically adopted first in industry?
Mm. Okay. Um, so the first error correction approach, likely to see practical, real industry adoption, is error mitigated early stage error correction, I would say. Not full fault tolerance, but like in some detail, like techniques like zero noise extrapolation, uh, probabilistic error correction, and measurement error correction mitigation will continue to dominate because they worked on today's like hardware and give real performance improvements without recurring like millions of physical qubits. These are already like used in industry pilots, as I like personally witnessed them with different kinds of platforms. But like just to also share what could be also like expected and thought across the industry is, I would say, surface codes. So for like the true fault tolerant quantum computing, the leading architecture is the surface code, and like the reasons for that could be said like it works well with 2D qubit layouts. It has like high threshold of error rates, and it matches with superconducting and trapped ion roadmaps coming from like IBM, Google, Quantinuum. Um, so like as the bottom line, I would say in the near term, 0 to 5 years, error mitigation and smaller corrected logical qubits, and in the midterm, I would say surface code logical qubits becoming like a semi-standard, but so far we're probably going to stick with that.
Great. So I have another question. From your experience, what are some successful examples of ecosystem building that emerging regions like Latin America could learn from or adapt?
Mhm. So that's a really nice question. Thank you for bringing that up. That's actually depending on like in which orientation you would like to create that ecosystem. So with QCAN, we wanted to have things as global. We wanted to make it basically going for everyone, both individuals with no background, just knowing some basic algebra, but nothing about quantum computing, nor computer science, and just wanted to get into quantum computing. So we have some interactive programs for them, but also for experienced members, for PhDs, professionals, just know many things about quantum computing, especially about theory, like the concepts that we talked about this presentation in the first place. But they just want to get the sense of how it feels to actually execute actual quantum tasks on quantum computers, to see some use cases. So we also have the licenses and specifically oriented like quantum optimization, quantum for finance, quantum for logistics problems for them too. So it's basically depending on your goal in that end. But if you're actually talking about the community side, that's also like a whole new aspect, because with Q Notebook and Q Network, we have like a dedicated space to actually make sure that it's relevant to community, it's relevant to what's going on with the industry, and how are we continuously making that interesting and impressive for everyone. So I believe that like the first starting point would be about learning, because this goes for everyone. I believe like anyone with the curiosity for science love learning new things. And the second part, like the one that comes right after that, would be about making it interesting for different kinds of backgrounds. People from all over the world, they're just merging for one goal, but they have different kinds of background. So it's key to make it interesting and compelling for everyone there.
So that leads to another question. So you are talking about being quantum ready, and so what do you think that means for an institution, for a company, for an individual, for an organization? What makes someone quantum ready?
So it's about like being quantum ready from the enterprise, the institutional way, or the personal way. So I would say being quantum ready means like an institution has built the capacity to understand, evaluate, and adopt quantum technologies as they mature. Because we're currently in a spectrum right now. Like we don't have a place where quantum computers are fully evolved and we're just going to integrate it into our system. It like doesn't mean that owning a quantum computer, it means actually having the foundations in place so that when quantum capability becomes commercially useful, and we're getting there, the organization can act immediately instead of like starting from zero. So like there are many core elements. It's about workforce literacy. It's about having a baseline, understanding across technical and strategic teams what quantum can and cannot do. Also separating the hype and what's real in there too. It goes for everywhere. It's about like identifying high value use cases. It's about looking into classical and quantum workflows. Maybe vendor and platform awareness, because if you want to adopt being quantum ready, it goes for either for individuals or enterprises, large companies, right? The luckily like there are not too many companies or platforms in quantum there, so it has like both pros and cons. The pro one is you actually don't have to just like lose around to just like being more comfortable with using the industry tools, with like a research, with access to some licenses, some seeing use cases, you would be able to actually navigate over different platforms and have that awareness. At least when we get into the commercial phase, know what to do when a certain breakthrough or advantage is coming there. So it's about like thinking ahead, building skills now, and creating a pathway either for yourself or for your team.
Yeah, I really like that. And so we are coming to the last question. The next speaker is online. What would you say to, inspire students in Mexico and Latin America to believe that they can play an active role in the global quantum revolution?
Mhm. So, like my take in this especially, and this doesn't necessarily have to go for quantum. We're living in a remote and internet connected world, right? So when once you open up your computer, you can basically access anything, any learning resources. You can connect with different kinds of people in the world. Like for example, I'm studying in the UK. I'm currently in Turkey, and I'm having this meeting with you all. And I'm quite happy to do that in here. So for that, like actually being a part of a community is something important, and quantum industry is very wide open to that. So being in a group, or either creating a group, an organization for yourself. It can be for profit, it can be non-profit, but doing something about quantum computing. It's your choice of your own. It can be about like for QCAN, we chose being an ecosystem. We chose providing learning resources. We chose providing quantum services for individuals and enterprises. But you can also do like a reading club for quantum computing. You can just follow the recent articles, recent breakthroughs in quantum computing. It can be either from the perspective of technical side or the popular science side. But actually being in communication with people interested in the same area, it can even be as getting together as an organization, as a company, is something crucial there. So doing something and sharing it with the community, being with community, I would say is key there.
Thank you so much. I know there are more questions, so maybe reach out to others. Thank you so much again for this excellent talk and
Thank you so
yeah,
much.
yeah, and
Thank you so much, Sandra, for your compliment. If you have any like further questions afterwards, you can always contact me over my LinkedIn, or you can just email me or contact us over QCAN. Thank you for your kind compliments, and thank you for the hosting, Sandra.
thank you, and have a wonderful evening now. Huh? You are,
You too.
it is, at your time
Thank you.
zone it starts to be the evening. Yeah.